All right, so as we're rapidly approaching the end of the semester, we're looking ahead. Let's see. We'll do a group quiz on Monday. Your exam is April 23rd, unless you've arranged to take it on the 16th, which I think I've gotten everybody sorted out who's going to take it early. There are only 2 more masterings. There's one next Wednesday, then the one after Easter. That's it for homework. And then there's the final. So we are like 3 weeks from the end. Okay. All right, so my plan for today is to hopefully finish off some of these last discussion points about how we can relate E and KEQ. And Monday we'll finish this chapter. The 16th we'll start some chapter 19 stuff that won't be on the third exam. Then we'll have a review day, maybe we'll move on, depends on how fast I am. Exam, nuclear chemistry, end of the semester. So, let's talk about how E0 relates to KEQ. So, from last chapter, we know that delta G0 is equal to the negative RT ln of KEQ. So the question is, how then can I relate delta G, where's my notes? Delta G to E. All right, because we had on Wednesday. So if delta G equals negative RTL of KEQ, and delta G also equals negative NFE0, it means they are equal to each other. So if we are at 298 Kelvin, we're at a known temperature. What is R in my equations? Gas constant. Okay, what's T? Kelvin. What about N? Moles of electrons, F. Yeah, it's a constant, Faraday's constant. Which means R, T, and F will now all be constant. So I'll move all the things that are constant to one side with a few adjustments. ln of K. So if R, T, and F are all constants, these guys all in here, so as long as I'm 298, those constants together will always equal 0.0257 volts, which I can now plug those numbers in to my red circled area. We now have a relationship between E and K. So before we had a relationship between G and K and G and E, and now we have a new equation we can use to directly relate E and K. All right, so let's think about what this relationship can tell us. Put my thoughts up here in the corner. If I have an E greater than 0, am I spontaneous or not spontaneous? I'm spontaneous. If I have an E greater than 0, what must my value of K be? Greater than 1 or less than 1? Greater than 1. So if E is spontaneous, it's telling me I'm moving towards products. K then must also be greater than 1 because it tells me I am moving in the direction where products are greater than reactants, which you can mathematically see. If you have an ln of K where K is greater than 1, natural log of that will be a positive value. So tell me what n is again. All right, number of moles. Can that ever be a negative number? No. So I have a positive number over a positive number. Positive. If K is greater than 1, then this whole side is positive. So E0 is always positive if K is greater than 1. Okay, if I have an E0 less than 0, am I spontaneous or non-spontaneous? Non-spontaneous. So what must my value of K then be? Less than 1. If a K value is less than 1, do I have more products or more reactants? More reactants, right? It's the fraction, right? And the only way K can be less than 1 is if I have a greater denominator than a numerator. I'll pull it together. All right. So let's go ahead and, if you have your calculator, go ahead and fish one out. We're going to do some practice problems. It's really dark up here. I can do this down. Nope. Oh, there we go. That's better. All right, so here I have an equation that I would like to determine the Gibbs free energy and the equilibrium constant for. All right, so our methodology for these types of problems will have kind of a few steps. Oh, not splint. Split. There we go. I guess you could splint it, but we don't want to do that. Into two half reactions. So here's our equation. We need to first split into our two half reactions. Otherwise, we don't know number of moles of electrons. And we have to have it in two half reactions so that we can find our E0. So once we've done those parts, then we can use that E0 to find G and KEQ. All right, so this is my crazy reaction. First question, what half do you want to start with, the iron half or the nitrogen half? Iron. Good, good, we'll do that. Iron is my favorite element. All right, so I have 3 Fe2 pluses going to 3 Fe3 pluses. Is this an oxidation or a reduction? Oxidation, so I put the electrons as a product or a reactant. And how many do I need? I need 3, right? Because each iron is changing by +1, so I need 3 to match it. Do I need to do anything else to that equation? Does it need to be mass balanced, or is it all set? Okay, that one's done. All right, so we got this other crazy one over here. Forgot my states and matter. All right, so my question is, this must be the reduction reaction, right? We already did the oxidation. But there are a lot of possibilities of elements that are changing oxidation states. Realistically, there's only one. Right, but we have nitrogens and oxygens and hydrogens all floating around in there. How do I know which element is changing oxidation state? Oxygen and hydrogen don't change. If you are confused about oxidation states, I have a handy dandy worksheet on my website called Oxidation State Rules. It does. They do rule. But it's rules for oxidation states. And it'll lead you through like step 1, if it has a charge, that's its oxidation state. Step 2, if it's an element in its natural form, it's 0. Step 3, if it's bromine, chlorine, iodine, fluorine, just about always -1, unless stuck to an oxygen. Then next one down is H's and O's almost never change oxidation states, just as a general guideline. Because if I look over here in water, right, we assume oxygen's -2, which means we have 2 H's, which are each +1. Well, the H is +1 over here, so that hasn't changed the oxidation state. So what is a good guess as to who is changing oxidation states? Nitrogen. All right, so we have to figure out what its oxidation state is on one side compared to the other. All right, so here I have 3 oxygens. Oxygen normally has an oxidation state of -2, so I have 3 of them. Right, that section's -6. What must be the nitrogen so that the overall is -1? +5. Okay. Let's look at the other guy. We have this guy. What's the overall charge of NO? 0. So what must be the nitrogen? +2. So I've gone from 5 to +2. Is that a reduction? Okay, so then where do I put those electrons? As reactants, and how many do I need? 3. Is everything else balanced in that half? The hydrogen's balanced, the oxygen's balanced, the nitrogen's balanced. All right, so we're done. Do I need to do anything to combine these top and bottom? Would the electrons cancel out? The electrons would cancel out. I am done doing stuff. All right, so now let's find our E0. How do I find E0? It's what minus what? Okay. Is the oxidation at the cathode or the anode? Anode. All right, so then we go to our handy dandy table, which I will find momentarily. All right, so we're looking for iron +2. Iron +2 going iron +3. There we go. Oh, almost in focus. Oh, there we go. Iron 3 and an electron going iron 2. It's in the wrong direction. Do I need to change the sign? In my actual equation, I have 3 irons going to 3 irons and 3 electrons. Do I need to do anything to this value? No, don't do any of that. Don't. Definitely don't. All right, so this is 0.77 volts. All right, then I need to find... I brought my abridged version. So, oh, there it is. We got NO3 and 4 protons, 3 electrons, making this and this. Its value is 0.96. Let's see, what does that turn out to be? That's a 1. They're kind of squished together. All right, so is this reaction spontaneous as written? Yes, because I have a positive E0. Good. Now we're ready for, so we've done this, we've done this, and we've done that. So what is my value for N? 3. 3 electrons are on this side and that side. So they don't add and they don't multiply. It's just 3 total was needed to balance it. 0.19 volts. Let's see, how many significant figures do I get? 2. 10 to the... What are my units for this now? Joules. It's a negative delta G, so is that spontaneous or non-spontaneous? Spontaneous. Good. Good so far. Everybody's lining up correctly. All right, so now we're ready to find KEQ. We're going to use our equation that we just wrote, 0.0257 over N ln K. So how do I get rid of that natural log function? E. Does K have units? No, it is unitless. Is this K greater than or less than 1? A smidge bit greater than 1. Does that match up with our spontaneity for everything else? Good. They should all tell you the same piece of information. If it's spontaneous for E, then it should be spontaneous for G, then your K should be much greater than 1. Okay. Do you guys want to do another one? No? Feeling good about that? How are we feeling about balancing in acid and in hydroxides and everything else? Not good? Feeling bad about that? All right, why don't we do one where it requires some balancing, and then we'll do some calculations. All right, what if... Okay, let's see if we can... Let me find a good problem. Let's see. All right, let's do this. I think base is trickier, so we'll do it in base. All right, so we'll balance the following in base, and in the end, I want the KEQ of it. Here is my reaction. I think that's supposed to be the gas. Let me see here. Maybe it's aqueous. All right, so I have MnO4 combining with SO3 2- to make MnO2. And SO4 2-. Oh, that should be a solid. Sorry, solid. My handwriting's kind of sloppy in my notes. Solid. All right, so which half would you like to do first? The manganese half or the sulfur half? Manganese because it's written first? Okay. All right, so first thing we have to figure out is who is changing oxidation state. Is it the MnO4, or is it the Mn or the oxygen? Okay, does oxygen ever really change oxidation states? Not really. So it's probably not the oxygen, which means we have to figure out what the oxidation state is of the manganese. All right, so oxygen typically has what oxidation state? -2, so I have 4 of them, so how much would that have? -8. What's the overall charge of this compound? Okay, so what should Mn be? +7, okay. I have 2 oxygens over here, so what is the charge of this half? Okay, so then what must the Mn be if it's overall 0? Yep. All right, so I've gone from 7 to 4. Is that an oxidation or a reduction? That's a reduction, right, of decreased. So do I put the electrons on the products or the reactants? Products, and how many do I need to go from 7 to 4? 3. All right, so now let's talk about how to balance it in terms of mass, right? So in base, you first do it with waters and protons, and then we get rid of those protons with base. So I need to add some water. Always add the waters first. Rule of thumb, waters first. Over here I have 4 oxygens. Over here I have 2 oxygens. Where do I need to put the waters? Products or reactants? How many do I need? 2. I did not leave myself enough space. All right, so now are my oxygens balanced left and right? Looking good. All right, so now what do I need to do about these protons? How many protons do I have as products now? 4. How many do I need then as reactants? You would stop there if we were balancing an acid, but we're not. We're balancing in base. So how do I get rid of those protons? Add some hydroxides. How many hydroxides? Okay. Can I stop there? No, because now I've messed up my mass balance. All right, because I just added 4 OHs. So I have to add 4 to that side also. They do become water. I just ran out of space. I'm going to rewrite underneath. Oh, it's going to be super sloppy. So these guys, let me see if I can find a different color. How many waters does it make? 4. So let's rewrite it down here. What is one more step I can do to simplify this? Cancel what? Those waters. So those are all gone, and this changes to 2. All right, so now we're going to take a break, look at the other half reaction, and then come back to see how we can combine them. All right, so let's take a look at this half. All right, so I have 3 oxygens over here. How much total charge does that half of the molecule have? I have 3 oxygens, each worth -2. All right. is going from 4 to 6 in oxidation or reduction. Oxidation, okay. So then where do I put those electrons on the products or the reactants? Okay. And then how many electrons do I need to go from 4 to 6? 2. I think everyone feels fairly confident about that part. It's the balancing part that's a little trickier. All right, so I have 3 oxygens on this side and 4 oxygens on that side. Where do I put the waters? Okay, how many? Just 1. All right, so now I have to deal with these protons. How many protons do I need to add to the other side? 2. So then how many hydroxides should I add on this side? 2 also. Then how many hydroxides should I add to this side? All right, so we just made some water. So now I have all right, what's the final simplification step I need to do for this? Yeah, get rid of those waters. So that's gone, and I just have 1 of those. All right, so now I have this equation and this equation. Can I combine them as is? No. What do I need to do to the manganese equation? Multiply by 2. And then what do I need to do the sulfur equation? By 3. So it'll be really, really long, and then we'll cancel some stuff out. Write small. All right, looking at our brand new snazzy equation, what are some things that cancel out products and reactants? Okay, electrons are gone. Good. What else? Okay, these are all gone, and that's now 1. What else? One more thing. These hydroxides. All right, so good. We now have our balanced chemical equation that has the right number of moles of electrons in it. We're now ready to actually start solving some stuff. After all that, we're ready to start solving. All right, let me see if I can make some space. That's not a piece of paper I haven't written on yet. The bottom half of this. All right, so first we have to figure out E0. All right, so I need to find the half reaction that matches my reduction reaction here, the manganese, 3 electrons, 2 waters. So looking at my little sheet, this one up here, so the reduction 1.68. And then I need to find the sulfate one. Down here, which has a value of, what did I just say? That's 4, make sure it's the right one. All right, is that spontaneous as written? Yes. Okay, so now we're ready to go on and find delta G and our KEQ. right, so what would be N for this particular reaction? 6. What was that? We don't have to. We don't have to, but I figure while we're at it. 5, 7. That was 10 to the what? 2, 4, 5. All right, how is that for spontaneity? Good, looking good. All right, so now we're ready for K. So, let's see what that turns out to be. 8 times 6 divided by I'm guessing it's going to be big. Yep. Yeah, my calculator's angry, actually. Yeah. My calculator says this. Overflow error. So, it is so spontaneous. Maybe if you had a scientific calculator. Like one of the fancier TIs. No? Okay, still angry? Yeah.
1.147 times 10 to the 100.
Perfect.
If we don't have that handy.
I won't give you one that is this big. It was, I made this problem up off the top of my head, and so I really didn't know that it was going to be that big.
I'm just getting the same thing as the matching chemical.
Yeah, if it has overflowed that close to
I think so. I think so.
Okay.
Yeah. All right, how do we feel about that? Balancing, then finding E, then G, then K. Feeling better? Feeling better? All right. What have we been assuming about the concentrations when I have the 0 up there? What concentration is assumed? 1 molar. What if we're not at standard state?
We have a big problem.
We have a big problem. You know what we have? An equation to solve it. So if we're not at standard state, what if I'm no longer at 1 molar exactly, which, not surprisingly, happens a lot. It's very hard to be at 1 molar all the time. Well, E0 and G and all those guys must be affected because we're no longer at standard state, right? We don't have that 0 up there anymore. So, that's it. Okay. So the voltage must increase if we change our concentration of reactant to also increase. Right, because my reaction, if it's my reaction is spontaneous, and I give even more reactant, it'll make even more products, which means that if you're imagining the 2 beakers, right, if we're imagining this guy, if I have even more reactants, it means even more electrons are flowing past, which means the voltage has to increase because it's a measurement of how many electrons are going from one beaker to the other. So don't panic. We have the Nernst equation. Nernst, after Dr. Nernst. which, by the way, I'm reading this real fascinating book, which I know only I find fascinating. It's about how quantum mechanics were started. Apparently, fascinating. Physicists in the early 1900s were fist fighting about whose idea was correct, right? So the plum pudding model or the Bohr model, full out yelling fist fights about who was right because it was so controversial. And now we're like, it's clearly not the plum pudding model, obviously. 100 years later, we learn about that, right, in elementary school. They put the nucleus in the center, the electrons spin around the outside. Clearly. Super controversial early 1900s. Real interesting. So, Einstein was not a proponent. He originally thought that it had to be plum pudding because he couldn't experimentally determine the other versions to be correct, which we still can't actually find a difference. Like, we know quantum mechanics exist, and we know Newtonian mechanics exist. We can't prove that they're related at all. So you may have heard of string theory. String theory is the idea that you can kind of relate them. Still not exactly right either. So it's real interesting. Probably just for me, but side note. Anyway. All right, so before, right, we had this. Plus. Right, we had this equation from last chapter, which relates my standard state to my non-standard state through Q, where Q is anywhere but equilibrium. But we also know
and it's standard state at 0 when it's at equilibrium, so right format.
yes, yep. No, sorry, I got distracted. All right, so we know this is true. Right, we have our delta G 0 standard state. We can also write a similar equation for this. Right, my non-standard state is related to my non-standard state E. So standard state G is related to standard state E. Non-standard state G, non-standard state E. So, just like last chapter, non-standard state G is related to standard state through some adjustments to the fact that we're not at equilibrium, right? This is just plus or minus what standard state should be. We do the same thing for E. This is non-standard state E, which is equal to our standard state plus or minus the fact that we're not at equilibrium. A little bit more, a little bit less, right? This is just an adjustment. So, right, E is my cell voltage. E0 is my standard state cell voltage, which we figure out E0 from the tables. E has to be calculated separately. And we have the same guys here. We have the gas constant, temperature in Kelvin, number of moles of electrons, Faraday's constant, reaction quotient. We can do a similar thing to what we did a few minutes ago and combine the RT and F. So that may be a more useful version of the Nernst equation. As long as you're at 298 Kelvin, RT over F is a constant. All right, last thing today, let's think through what this equation means. Let's say we're at a state where I have a Q greater than 1. Do I have more reactants or more products? I have more products, right? If I have a Q greater than 1, then I have so then what's the natural log of Q? Will it be a positive number or a negative number? If you don't know, take your calculator and check real quick. Like, just do natural log of 5. Definitely positive. Natural log of 100. Still positive. So if this is going to be positive greater than 1, what's this whole half? This can n be a negative number? No, right? So I have a positive number times something greater than 1. What value is this going to be, positive or negative? Positive. So I'm going to have E equals E0 minus a positive number. So my final answer will be less than my standard state. Right, because if this is like 5, and my voltage is 2 minus 5, my final answer has to be smaller than where I started. All right, let's do the opposite case. If I have a Q less than 1, do I have more products or more reactants? Okay. So what's my natural log of Q value? Less than 1. So now I have a negative number times this. This side will be negative, but I'm subtracting a negative. So I'm really adding to it. So E is greater than E0. Well, if I'm at the point where Q equals 1, I'm at equilibrium. What's the natural log of Q equal? Right, so really I'm at the point where really Q equals K, which means I'm not at non-standard state anymore. I'm at standard state, which means I can use the equation with K in it. All right, we will stop there. We will finish the rest of chapter, whatever this is, 18. We'll finish that on Monday, so that those people taking the test early, you've covered everything that's going to be on the test. For those people not taking the test, we're going to move on to chapter 19 and do some nuclear chemistry, some other stuff, which will be on your version of the test. Yeah, hi. Oh yeah, that should be 0. Sorry, Ellen. Should be lesser or greater than 0. Yeah. Yeah. Yeah.